In question 3, they are giving us two graphs. The first one is a quadratic, and the second one is a horizontal line passing through 12. The interval that we're dealing with is along the x-axis, going from 0 to 3. If you look over here on the left, this is already the region. It's already graphed for us or nicely shaded out. This is the region that we're going to be revolving, and we're going to be revolving about the horizontal line passing through 12. So we're not going to be revolving around the x-axis. We're going to be revolving about this line right here. When we do that, this is the solid that we're going to get. You can perfectly imagine what's going on there. And we're going to be using that disk approach that we used in class in order to do this. Since there is no hole in the middle, then we're not going to use washers or anything. We're going to use a disk, and the cross section of the disk we know is a circle. Let me highlight over here. This circle right here is the cross section of the disk. The disk is not fully drawn. I can go ahead and try to do something right there. That will be your disk. All that I need is the cross section. And for the cross section, what I really need is the radius of that circle. And that shouldn't be that bad. So for example, the highest value is 12. And then this particular circle is going to be at a y value when it comes to a height. The height of that circle is going to be y. So then that means that the length of this tiny segment, which is the radius, is going to be the difference of 12 and y. So then little r, the radius of the circle, is going to be 12 minus y. And I know why. I know that the y that I'm talking about is this y right here that happens to be on the parabola. So then I'm going to go ahead and write 12 minus 9 minus x squared. That's going to give us 12 minus 9 plus x squared, which is going to be 3 plus x squared. So then we now know that the volume of this solid will be pi times the integral going from 0 to 3, because we are going to be integrating with respect to x, and I know that because the cross sections, if you look at the cross sections right now, they are vertical or perpendicular to the axis of revolution. So we're going to say the integral from 0 to 3 of the radius, 3 plus x squared, all of that squared, dx. And then what I would do here, if I want to continue now, this is the easy part. I will go ahead and expand that, get a polynomial, and then integrate each term at a time. In part B, they are now telling us to create our solid by revolving or rotating about the line y equals 15. If we go back to the left, you notice that 15 is above the region, completely above the region. There is now this gap over here. Well, when you do the rotation, this gap will turn into a hole inside of the solid. As I was saying in class today, you can go ahead and stick your hand in and go from one end to the other. So then we're going to use the washer approach. In other words, the cross section of every single disc is going to be a washer, because every single disc is going to have a hole inside. So when you look at the cross section of those discs with the holes, you're going to see a washer. That means that if we're going to use the washer approach, we need the inner radius and we need the outer radius. So if you now go back to this diagram here on the far right, you're going to see pretty much a diagram of the region. So notice how the washer is already done for us. You can see it right here. This piece over here, this piece here And no, let me do that more carefully. So that's going to be, no, that's right, here and here. What I need is to be able to figure out the inner radius. So in order to do that, let me call that R sub I for the inner. The inner radius is going to go always from the axis of revolution to the first function that you touch. And the first one that I touch is the horizontal function, y equals 12. So then this particular length will be the inner radius, the smaller radius. I can easily get that by taking 15 and subtracting 12. That's going to give me 3 units. Now for the outer radius, again, I go from the axis of revolution to the outer graph right here, which is the parabola. So the outer radius will be 15 minus y. In other words, 15 minus 9 minus x squared, which is going to be 15 minus 9 plus x squared. That's going to give us 6 plus x squared. So now that I have that, I can go ahead and start forming the volume. Then the volume will be pi, the integral from 0 to 3, are the outer radius squared minus the inner radius squared, all of this dx, because we are integrating with respect to x. All of these cross sections are perpendicular to the axis of revolution. That's going to be pi, the integral from 0 to 3. Now substituting the formulas, we're going to have here the first one, the outer, 6 plus x squared minus 3 squared, and then dx. What I would do now is I would go ahead and expand this and then integrate a term at a time. Example 4 is asking us to find the volume of the solid that will be obtained by rotating the region that is bounded between the quadratic, right here, the graph in green, and the line y equals x, right here. So you can see the region again in this light brown. But this time we are going to be revolving about the line x equals -1. And this was given in the problem. If you notice, I drew that line over here in blue. This is going to be now our axis of rotation. So when I take this region and I revolve it about this line, I am going to get some other part right here, and then I'll be able to form my solid. So it will look, let's see if we can get that. This point over here is going to be reflected to some point right there. Then I'm going to have this straight line, let's say something like this. And then right here underneath, we're going to have the piece of the parabola. I mean, it's not perfect, it's not identical, but I think it's okay. Then, because there is a gap, notice over here, this gap from the axis of rotation to the y-axis, when we create the solid, now you're going to have something like a tube inside. You're going to have a hole inside. Again, you'll be able to stick your hand through that solid and exit in the other direction. Now, I will not try to draw the solid. That's going to get too messy and too complicated. All I'm going to do then is to draw the washer, because remember, as soon as you get a hole inside of a solid, you use the washer method. So you find the area of that washer. Now, because we are rotating vertically about the line x equals -1, my washer will begin from a horizontal tiny segment. If you remember when we were rotating about the x-axis, you start with a segment, a tiny little segment that is perpendicular to the axis of rotation. Now, to be perpendicular to the axis of rotation, this tiny segment has to be horizontal. Same thing over here in the other direction. Then if I form the washer, I'm going to have this piece connecting here, this piece right here, that's going to go over here, and this one is going to go below. Okay. Not the best washer, but all right. Then what I need is to figure out, again, going to the original graph, I need to figure out the inner radius. That's going to go from the axis of rotation all the way to the first graph that we encounter. So that's going to be r sub I. And if you notice, r sub I is going to travel 1 unit. The distance from the axis of revolution to the y-axis is 1 unit. And then we're going to go a little bit more. That's going to be x. So r sub I will be 1 plus x. And because we are integrating here with respect to y, and since x is equal to y, then I can replace x with y, right? Y is equal to x, so I can do a direct substitution, 1 plus y. Then for the outer radius, I'm going to go again from the axis of revolution all the way to the outermost graph. That happens to be the parabola. Then remember again, we're going to have to re-express everything in terms of y. So then we know the square root of y is equal to x. I'm only going to worry about the positive because we're talking about length. Then this is going to be over here, again, 1 plus x, which is going to be 1 plus the square root of y. Now that I have all of that, I can set up my volume. The volume is going to be pi times the integral, and we are going to be integrating. Let's see, we may have to find that out. So I need to find the point of intersection of those two graphs. So then I'm going to set y equals x equals, and y equals x squared. I'm going to set them equal to each other. So when will x squared equal to x? That means x squared minus x is equal to 0. X times x minus 1 is equal to 0. That implies when x is equal to 0 and when x is equal to 1. So then I know that this value is going to be equal to 1, which means that the y value, when x is equal to 1, 1 squared is 1. So that's going to be 1 as well. That means that we're going to be going from 0 all the way to 1, and I'm thinking about that in terms of the y-axis. From 0 to 1, the outer radius squared minus the inner radius squared, all of this dy. So then pi, the integral from 0 to 1, the outer radius is 1 plus the square root of y squared minus the inner radius, that will be 1 plus y squared, brackets, dy. And as before, if I carry on this integration, I would go ahead and expand these binomials and then integrate a term at a time. The final answer here, once you work everything out, should be pi over 2. It is definitely a good exercise for you if you want to go ahead and see whether you get pi over 2 as an answer. In question 5, they're asking us again to find the volume of the solid obtained by rotating the region that we see right here on the left about the line x equals 2. If you notice, we have a gap from the region to the vertical line. This is telling us that when we create the solid, we're going to have an empty space in the middle, and we're going to use the washer method. So the washer is, so the shape of a washer is going to be the cross-sectional area of these discs. Same idea as in all of the previous problems, pretty much. Now, in order to create the reflection, let me go ahead and try to generate something similar. That's what we have over here. That means that we're going to go all the way to 4. We're going to have something straight like this. And then this part is going to go up. Maybe a little bit of more height. This is going to go up like this, down like this. So imagine a perfect reflection. And then because we are going to be reflecting about a vertical line, then the washers are going to come from a tiny horizontal segment like this. Let me go a little bit higher, like that. And then that is going to reflect over here as well. So to create the first washer, go from inner to inner, and then outer to outer. There it is. And what we have to do again is to go ahead and get the inner radius and the outer radius. Ladies, the only thing different here is that when you pass, I'm going to draw this in red, when you pass this segment right here, and let's say you were to draw another washer, if you notice now, this segment is touching a different function. This one is different from the one above. So past the mark, let's say of 15, if you go from 15 to 16, you are dealing with this line over here that is decreasing. But whenever you go and you look at washers that are below 15, so from 12 to 15, you're going to be dealing with this increasing graph. That means that we're going to have to calculate two separate integrals in order to calculate the volume. A piece of the volume is going to come from the washers that are going to use this line over here, the one that is decreasing, and then the other volume, the other piece of the volume is going to come from this graph over here that is increasing. So to start finding the radius, we're going to do the upper part along the y-axis. We're going to go from 15 to 16, and then we're going to do the bottom part. If you remember, let me take you back over here. I am looking at this horizontal blue segment. So to find the radius, the inner radius, I go to my y-axis, and then I go across until I touch the first graph. So look at this black segment over here. This is the radius of the inner circle. So in order to find that length, r sub I, the inner radius, that's going to be pretty much 2 minus the length of the blue segment. And that blue segment is positioned at some unknown x. So 2 minus x. As soon as I notice that we're integrating with respect to y, that means that we're going to have to take this function with the negative slope and re-express it in terms of y. But that is as easy movements of the x and the y terms. If I know that y is equal to 16 minus x, then that means that x will be equal to 16 minus y. So going back to the inner radius, we're going to have 2 minus 16 minus y. That's going to be 2 minus 16 plus y. That is going to give us negative 14 plus y. So let me write y minus 14. That's going to be the inner radius. And now for the outer radius, r sub o. For the outer radius, we're going to go again from the axis of symmetry all the way to the end. That means exactly 2. So that was an easy one. That's going to be 2 right there. So now that we have inner radius and outer radius, we know that the first volume, let's call it v sub 1, will be pi, the integral from 15 to 16 of the outer radius squared minus the inner radius, y minus 14 squared dy. Now, let's go ahead and do the same thing with the bottom part. So by bottom, I mean from, right here, if you look at the graph, from 12 to 15. So this is now my interval of interest. Now we're going to look at the interval from 12 to 15. And when we do that, same analysis, the inner radius, I'm going to do that in yellow right here. That is, let's say that's going to go, if I'm using this horizontal segment, that's going to go from the axis of symmetry all the way to the first graph. That means that we are going to have practically the same thing. We're going to have 2 minus an arbitrary x, but now instead of using the line with negative slope, we're going to use the line with a positive slope. That means y is equal to 3x plus 12. Whenever we solve for x, x is going to be equal to 1/3 y minus 4. So then going back to the inner radius, that will be 2 minus 1/3 y minus 4, which is going to give us 2 minus 1/3 y plus 4. That will be 6 minus 1/3 y. So that becomes r sub I. Now that I have that, I will try to find out what is the outer radius. That will not change. That will remain being 2. So then volume sub 2, the second volume, will be pi, the integral from 12 to 15, and then the outer radius, 2 squared, minus the inner radius, 6 minus 1/3 y, all of this squared dy. So, conclusion, the total volume, I'm going backwards here on the left, will be V1 plus V2. So then that means that we're going to have, if we put all the integrals together, that's going to be pi, the integral from 15 to 16 of 2 squared minus y minus 14 squared dy plus the integral from 12 to 15. Let me put pi there as well. Brackets, 2 squared minus 6 minus 1/3 y squared dy. Then, again, you will have to expand those binomials and then integrate each term at a time. But that will give you the total volume.